okay, whatever you are going to, whatever I'm going to discuss here is generally like industry part. So don't try to like, or don't like try to puzzle yourself that okay, maybe I'm not quite related with the topic or I'm not quite connected with the topic. I'll try to discuss as much as possible, but like this is a very like a vast topic, a vast domain. Even like the expert in this field is not expert enough, even spending like 40 or 50 years of their like how I can say it, like the life in this industry. So okay, so quickly go to the next slide. Okay, so here, okay, we are in an era, like this is like right now going through the evolution of artificial intelligence. Is a very exciting topic, exciting domain, and many of us we are trying to use AI as a tool in our daily job, right? Like in our daily application. So industry has its own perspective, academician has its own perspective. So I'll try to catch this both industry into one into one topic. So to know about AI, first will be the fascinating story of okay how AI has been evolved, and what is the similarities and dissimilarities from where it has been mimicked, like from a human brain, right? So this is an evolution story. And one thing, like if you have any question, feel free to ask me, and or you can drop also your questions to your message box. So yeah, so the story has been evolving. You can say roughly in the year of 1950, we know about the perceptron, right? And also like in 2015, when I was pursuing a PhD, that time also like we didn't see a booming of this topic there, but after that one, we see a significant booming in this topic. So we started our story from artificial narrow intelligence. So what is artificial narrow intelligence? Is mainly you have a specific task. So for that task, you have a specific model. So suppose like you want to do a risk analysis in the finance industry. So you have a model, but also that model can solve only one particular task. So the main problem or the main drawback that scientists or we have seen in this kind of model is it requires a gigantic pool of data, right? Like as for the supervised learning, you need really to teach this model. You need a diverse and a very significant amount of data to teach that model. And definitely that means it is complying with the high demand of processing power. You need quite a lot of GPUs, and you need quite of like a current, of course, like the processing power to really train these models. So then right now we are living, you can say, the interface of artificial general intelligence, and our goal is to reach the paradigm of artificial superintelligence. So you can think of like, okay, is a Terminator, what we have seen in Arnold Schwarzenegger's movie, right? So, but if I try to formulate this idea in a mathematical model, right? So what is ANI, what is AGI, and what is ASI? And the question is also like, okay, can we ever reach the level of ASI or not? That is also like, if you think about a mathematical model, so you can see that is depicted by this graph, right? And that graph is being limited by base error. So what is base error? You can think of an example that, okay, in your exam, your full marks is always 100, right? And now in your entire class, maybe someone has got a mark of like say 99.91, and someone has got a mark of say like as I said, like definitely there's no decimal mark, but here for we are assuming that okay, there is a decimal point. So 99.91, and student B has received 99.81. Now if I come back to you and ask, okay, who is better? So the relative, so there's no specific answer, right? Because both have got a 99.91 and 99.81. So only the difference is between in the decimal points. Now, if I ask you the relative question that who is better, definitely you will get the highest limit of 100, and then you are going to subtract 99.91 and 99.81, and that metric is basically defining who is better than the other. Now, if I raise that bar of 100 to 1000, right, and now if I take the same subtraction, 1000 minus 99.81 and 99.91, and if I try to plot a graph, you'll see that both are coming almost in the same vicinity or in the same area, right? right? So base error is, you can think of like an imaginary number that nobody can ever achieve in their whole lifetime, right? It is always like an imaginary number, like infinity. Okay. So we are the smartest creature in the world. So we always try to, like optimize this difference by our error limitation. So if we think about a model that can someday surpass the point of here, uh, just a minute, yeah, in this point, in that case, you already achieved, I can say that mathematically, again, or theoretically, is AGI. And when your model has surpassed this limitation and towards achieving more and more close to base error, that means you have achieved the paradigm of ASI, or artificial superintelligence. Okay. Now, if I see a story of like how our human brain has been evolved. So what we are today, how smart we are today, is defined by 2 million years of evolution of a human brain. And in your cortex, is 16.33 billion of neurons. Is basically what is defined by you. So we all are individuals, right? So our individuality is defined by your own brain. Okay. And that has been evolved over 2 million of years. That is defined by your consciousness, smartness, whatever the different attributes of a human personal it is. In contrast to that, if I see what is the evolution of AI or whatever AGI we are talking about today, that is only an evolution of 74 years, starting from perceptron to the GPT-4 or even DeepSeek, which has been recently published, right? So GPT-4 has 1.76 trillion of parameters. Okay, so you can see that, okay, there's a lot quite contrast between what is the actual neural network, which is human brain, and what is the artificial neural network, and we can see this calibration. So that means, okay, we can reach somewhere if we try to evolve our artificial neural network. Maybe someday it can surpass that intelligence level of what is being achieved by a human over 2 million of years today. Okay. So next question that we try to find out, because we didn't want to use AI just because of it's a buzzword, right? And it is not for only semiconductor. It can be for any domain. If you're a researcher, you always have to find out the answer that, okay, why I need AI? Can I solve the problem without using AI or not? That is the main vital question that you have to ask. So we try to define this statement over the problem we have in the industry. So we know that the technology roadmap right now, we are heading towards, again, don't go into my definition of no technology. That is quite critical. It is just like I have to refer. So we are standing in a domain where going towards 2 nanometer and beyond technology node. So technology node, the definition has started with the definition of, we all know transistor, right? So transistor has a gate length, right, or channel, which is like mainly responsible for surpassing the current. So we started when the technology roadmap started. The definition, it follows that how much we can squeeze the gate length so that the transistor become double, following Moore's law, like each and every 2.5 years, your number of transistors in a chip is becoming double mainly. Right now, we cannot follow the trend because we have already reached a few years back the physical limit. But still, we are trying to make progression on keep surviving Moore's law, right? And of course, like we are following right now the quantum gates and quantum circuits. Quantum machine learning is the next trend, because we already have reached the physical limit of a device right now. But still, as I said, like we are looking for some disruptive technologies, some new innovation ideas, how we can push Moore's law beyond what it is today. Okay. So what the main problem is that, okay, we know the technology roadmap why we are going ahead. As I said, 2 nanometer and beyond, and we are talking right now. If you followed some of the recent study, Intel is following 18 nanometer technology roadmap. So you can imagine, like, okay, a device which is even less than an atom, which is surely not possible. So we have our own definition of this technology node definition. But yeah, one thing is inevitable is that means with this technology roadmap, the future is defined by the increased device complexity, which requires increased process control. So process control, again, I'm not going into much detail. Process control means like, okay, you have different spec, you have different constraint when you are going to say print that chip into the silicon wafer, right? We have a blank wafer. You generally design a chip, and then you follow some process steps, which I'll show you in my later slides. And then basically by controlling these process steps and the constraint and the parameters, we generally get that device printed into our wafer. Okay, so in between, we need the accurate metrology and data analysis methods. We analyze a huge volume of data to generally optimize this complex process flow. Okay, so right now the industry is driving the force mainly in three innovation strategies. One is multi-patterning, one is UV, and one is direct cell assembly. So I will not go into much detail of these three phases. It's just like for you can see that how the complexity is increasing for these innovation stages. Okay. Now we can follow a nice video from ASML. What on the UV and high-end UV. Okay. So let's see. Can you follow the video? Shomindu, can you follow the video?
Yes, sir.
Okay,
Yes.
okay.
Yes, visible, sir.
There is no audio actually.
Hello, sir.
Yes.
Sir, actually, is it video? Because we can just see it, but no audio is there, I guess.
I'm not sure because audio is not in my control because I can
Okay, sir. Okay.
I have the audio from my side, so I'm not sure what happened. But yeah, it's nothing important. Like you just have follow the video. Like I just tried to show you some of the video of high-NA. You can search YouTube like ASML high-NA UVL or UVL, and you can watch the video. So
yes,
what I just have to try to show you here is what is the complexity level of this one tool, and this tool generally costs few $1 million, right? So this tool is basically responsible for printing the device that you have designed in your computer, putting it into a chip. Okay. And the complexity, to understand the complexity level of this tool, if you have seen that, okay, this is generating the UV light, right? You have seen like there's a purple light, which is the UV light. To generate this light only, which is responsible for printing the device, you need to hit 50,000 droplets per second. So that means there is a droplet of a chemical or water, and it has to be hit by the light source. 50,000 droplets has to be generated to induce or to generate this source. So you can now imagine that how complex this process is going to be. Okay. Okay. So now, okay, what are the challenges in metrology and inspection? So you can think about, if you don't know about, okay, I can imagine that you don't have the domain knowledge of this thing, so don't feel guilty. So just try to understand that metrology and inspection of the process control is basically that to keep your all this process or all these steps into a constraint. So we generally do metrology and inspection so that we can individually inspect that something is going wrong or not, or something is beyond your expected spec or not. Okay, and if yes, so then we have to do a lot of re-engineering and rework, and if not, then we go for the next process level or the next process stage. Okay, towards like what you find in your mobile or in your device, which is a packet chip. Uh, so yeah, so that is what we found that okay, we need not only a simple metrology technique but hybrid metrology. We have tried to define hybrid metrology. And what is hybrid metrology? It basically encompasses all the different origin of data from the different process, from the different tools, from the different specs. Okay, from the different stages, and we generally try to interconnect all these information into one, and then generally we derive the knowledge. I'll show you in my later slides. Yeah, that is what I was talking about. So why we need ML? Once again, we come back to the same question. So now you can see that we have generally 4 basic stage of data generation. One is called process log. This process log is basically coming from the tool, from the hardware part, from your recipe, from your process. Okay. Fab metrology inspection is basically like your metrology data. As I said, like okay, if you have a design, say your gate length is say 20 nanometer or 30 nanometer. So we do a lot of measurement in the intermediate step. We also collect the overlay data, metrology data, lineage roughness, line width roughness, contour extraction. So that is basically metrology data. Lab metrology is basically you do a lot of like XRD, like TEM acquisitions, SIMS, Raman effect. All this data is coming from generally, the inspection also, and then you did a lot of simulations. So simulation means like okay, what are the different process steps that I will generally combine to generally define the process, and if what is your spec length in this. So this is kind of simulation that you do, and generally now you can imagine that it is not possible for a human being or even a team of human being to analyze this large volume of data, right? So you need something, and also like the main limitation of a human being analysis is you cannot see a data beyond 3 dimension. Okay, we are talking about 4 dimension, but generally in your brain you cannot perceive a data beyond 3 dimension, and so it's a simple sentence that what you cannot visualize, you cannot analyze, right? So we need a powerful tool that can mitigate this problem and that can analyze data beyond 3 dimension. Okay. So now, okay, now the problem of the AI. So till now we defined the challenges in the problem domain. Now we also have to think about, is it very straightforward method to utilize AI in an industry concept, not in academia concept, right? So what are the challenges in AI to be developed? Okay, so now we can see what can be the challenges. So I showed some of the critical tool here under some process step like ALD, atomic layer deposition, CMP, chemical mechanical polishing, H, metrology and inspection. So we are generally generating this data with 4 challenges of V: high veracity, high variety, high velocity, and high volume. So for a metric, each and every second worldwide, you are basically generating few petabytes or few terabytes of data from the different IDMs, from the different foundries. Okay, so you have this raw data, and now imagine that okay, you are going to build a model. Okay, but okay, you did some feature extraction and data analysis also, of course with the help of the domain expert, because you need the domain expert knowledge like a physicist, chemist, resist vendors, tool vendor. So you have this kind of knowledge. Your target specific domain has been said that this is a process-centric problem or a problem-specific problem. But if I ask you now, can you tell me what kind of ML model or AI model is suitable for solving this task? So yeah, let's see. Okay, it can be a ranking model, it can be a regression model, it can be a recommender system, it can be clustering, it can be an anomaly detection, and it can be a classification. So this is all the model that you have heard about, right? But in this problem or in this situation, not only a single model is helpful for you. So basically then on the AI domain, you have to think about a framework. It's not a model anymore. You have to framework which support multimodal machine learning, and that also has to be adaptive. Okay, you cannot just go and change some model for some application base. That is what I discussed in my previous slide, that ANI through AGI, and you are trying to go to ASI. So if you have to achieve AGI and ASI, that means you need on your side a multimodal machine learning support, that the model can think by itself, not by a human expertise. So we are talking more about the unsupervised part of the model, or generative part of the model. Okay. So what we found is, now if you say you solve the problem with a machine learning model, now you go to the tool vendor, or say the venture capitalist. That's okay. I need the funding, and what I do is, okay, if I have some problem I found in the tool or in my process review, I'll just simply change the tool. The tool just you have seen in the video, and that one tool has been developed over definitely 5 to 10 years of research study, which costs few million or multi-million dollar. Now, if you come back to me that, okay, I found some problem in this tool, and now I want to develop a new tool, right? That is not possible. Nobody will entertain your request. But what you can do, or what we have tried to do, is we took the same model, or we took the same tool, and now we implement a model, or we're trying to implement a model. There you can pass your raw data. Will do the analysis by itself, and the model will pass on an improved knowledge back to the user. So that means you can reuse this model again and again, no matter how many different technology you are passing through, or what many different. Also, that this model is so generalized that you can plug in any of your tool, any of your parameter there to extract the improved knowledge transfer. Okay, so to understand, so we did a study that what is the existing solution. Basically, we're not the first one who are going to propose on the machine learning application, right? So we studied throughout our year at IMEC, and what we found is it is not only applicable for semiconductor. It is generally applicable for any domain. You found that this is the generic structure of the machine learning model. We focus on the model-centric ML applications. Anybody heard about model-centric paradigm? Anyone? Yes, no? Okay, so model-centric application means you generally take a model, like say you want to do an object detection, right? So you go into Google, you search about say ResNet, say YOLO, right? And YOLO also have different variations, like starting from YOLO 1 to till now, I think YOLO 11, or YOLO NAS. So you choose a model, but if I ask you that why you choose a model, you maybe don't have a specific answer. You can say that, okay, this model I know is very popular, everyone is using, so I'm using it. So if you are doing this, that means you are falling under the paradigm of model-centric approach. So what you do, you have collected your data, you did your data processing, you have your modeling, you do the conventional training, you did some further evaluation, right? Based on the evaluation, if you see there's some problem, you generally tuning your hyperparameter. You do some further training with some additional data maybe, and once it is performing expectedly, you generally take it for the deployment, right? But what is the problem in any manufacturing domain or in industry is mainly you need a high level of customization of this kind of paradigm. Okay, what is the main problem? The main problem is each manufactured product would require a distinctly trained model, and we cannot follow such a template in terms of size, right? Say suppose like if you have 50 different problems and you build 50 different models, and you can imagine like for an industry, the problem is changing each and every second, right? So that means each and every day maybe I have to develop, or my team has to develop few thousands of model and its successor or predecessor versions. And also I have to keep the data for each and every specific training. So that means to build a machine learning model, basically I have to build a warehouse, which maybe sometimes will burst with its volume and size in industry level. So that kind of template we cannot follow, right? Another main drawback is you need a large data set. That I said in this paradigm, you need a huge data set to generally train the model. Now, in case of an industry, the relevant data is not just rare and noisy, but also extremely expensive to get. The tool I showed you, if you have to rent that tool for 1 hour, you have to spend 5,000 to 6,000 or more dollar per hour, right? So that means if you have to acquire the data, maybe you need 10 to 20 hours. I'm just giving a numeric figure here, but it's beyond that. So now you can imagine that in 20 hours or 10 hours of requisition, how many dollars you have to spend for just to acquire the data. You have not even built a model, right? So now what is the problem in the model-centric approach more is if you see that most of the models are supervised or semi-supervised, that means you have multiple models for multiple applications. It requires offline training. So all the training you are doing basically is offline. You generally have your data in your local computer, you build a model, you train that one, and then you generally deploy it. But by the time, in industry case, if you think about the time you have deployed the model, it basically has changed the problem domain itself, because this is online, this is dynamic, right? It heavily depended on metadata and became, that means you need a process expert to stand and sit with you to generally explain you, okay, what has gone wrong. Because if you are not a domain expert, possibly you cannot understand fully what is the source of the data and what are the features of the data by itself, right? And then if you will build a model, basically, which is heavily dependent on the process, the domain expert. For an example, again, if you think about a simple problem, that, okay, I have given you image of an apple, say 100 image of an apple, right, to train a model. You generally train a model, you want to build a classifier, and the model can be generally classify it, okay, I'm seeing an apple. But what if I change the definition of apple? Say I'm the expert, I give you the image of an apple, but I tagged it as an orange. What will happen? Your model is so perfect, right? But it will classify all the images of apple as orange, right? If you agree with me, right? If you teach the model an apple as an orange or the vice versa, orange as an apple, your model is supposed to do that, and that you don't want. So that is learn from the given data. It can only learn whatever you are going to tell him. But in human brain or as a human, we are not like that, right? We have our own perception, we have our own understanding. Okay, for an example, if you go to a different continent or a different country, say something like you have never seen in your whole life an apple can be green sometimes, right? Or apple is completely yellow. We have never seen in or completely black, say. But still, if you encounter such a problem, if you think about how your brain is working, is okay, what the feature I'm seeing or what the object I'm seeing is very close to an apple, and then you are going to make a metric of similarities and dissimilarities, that okay, whatever the known features of an apple, I know I am seeing all these features, say 10 features are very similar to an apple, and 2 features are very different than an apple. And maybe color is the main attribute there. But still you can build a knowledge reasoning based on the data you have without supervising. So that kind of model that we are thinking about across a different domain. Right now, the scientists are talking about, as I said, this is the main principle driving behind AGI to ASI. Okay, and one of the main problem of all these model-centric approaches, they go under catastrophic forgetting, and sometimes we human beings also undergo such scenario. I'll show you in one of the example. Okay, so try to understand this problem with a simple example here. Say defect classification. I want to classify some defect. It is something like, okay, you want to classify some, say, object, right, like cat and dog. And instead of cat and dog, here we are terming it as defect. So I have 1,000 images of different defect types. You don't have to know the name of the defect, say A, B, C, D, E, okay? And again, I'll come to the same question, that can a human being classify this defect? The answer is yes, he can. He surely can. No machine can beat human being till death, okay? So I can think of like, okay, the expert has classified all the image, but now I change the problem in a different context. Instead of 1,000 image, I'm giving him, say, 10,000 image. Again, I'm asking the same question. Can he classify this defect for me? Answer is yes, but he requires a lot more time, right? Now, if I change the constraint again, that from 10,000, if I give you 10 millions of images to classify, again, you can, but you need now maybe not a single human expert, but a team of experts. But still, that means it is proportionally constant with the cost and time involved. Now, in any manufacturing industry, the cost and time is basically is huge, right? Because till the time you are not going to classify or not going to identify this defect, your entire future production steps are in halt. Okay, we are waiting for this result to come to us. We'll do further analysis, and then only we can proceed. Okay, and what is the significance of this defect? So what you are seeing in terms of defect is basically these are the metal lines. So in your chip, right now we don't go for external wiring within the chip. We embed generally the metal lines. So you are seeing here the metal lines passing through your device, and the first one is basically when two lines has been shorted. The next one is basically your line is your copper line or your metal line is broken. Okay, your line is becoming narrowing down, and the different variations of say the bridge and the micro bridges. So that means you can imagine now you don't want an iPhone which is quite lakhs of rupees in cost generally fail, right? So you bought a phone today and tomorrow it is not working. So you don't need that one. And you can imagine that if it occurs 1 out of few millions, then also it is a critical problem for the entire device. So that is called the definition of yield, right? We heard about the yield. So we need 99.99999, and mostly, as I said, you cannot reach 100%. So 99.99999 something more decimal points is basically the yield you are looking for. Okay, so you can imagine that how critical it is that you can detect these defects in early stages. And there's not only 5 different defects, there can be 1,000 and more, that one. So definitely, the resolution is, okay, we can build a smart model that can replace this human being, right? What I have to do, I have to do some annotation, I will do the training, and now my model can identify all the defects, say for assumption. But the next question that you have to answer is, what if the new defect types are being introduced tomorrow? It can happen because we are talking about a stochastic event, right? So there's always the possibility, because you are always inventing new materials, you are always inventing new other disruptive technologies. So we started from 1D, 2D, 2.5D, 3D. We are now talking about chiplets, right? So that means you are basically vertically growing your chip, not in 2 dimension, but in 3 dimension. So these all critical challenges or the innovative technologies are producing more and more challenges. And one of the definite problem is you can introduce new defect types tomorrow, okay? What will happen in that case? Definitely you have to retrain your model. Answer, okay. What if the trained model works well with certain defects, but fail for others? This is also, you cannot guarantee. You took a model, say suppose like you have apple, orange, banana, right? So you have 5 or 10 different types of objects that you have to, but you cannot guarantee that what the model you have developed by hyperparameter tuning, your model will classify each and every different objects with 100% accuracy. It cannot happen, even if you have seen in your plug and play, right? Again, this problem cannot be sustainable in an industry level, right? So we have to find an answer that, okay, what you will do if your model can identify 3 of the defects and fail for the other 2? Okay, what is our answer? You have to think. Okay, can you use the same model for denoising and extracting? So that means what I wanted to mean here is, can you use this model for other different tasks? Answer is no, I cannot use, because as I said, this is n is to n, multiple model, multiple applications. But what we need is one model, multiple application. So in computer science, it is you are trying to solve basically an NP-hard problem, right? Like 1 to n. Can we detect the defects without anchors, design details? That means, can you detect these defects without the help of any metadata or become dependency or not? That means, can we exclude the use of domain expert knowledge or not? Okay, what if we change the field of view, the contrast, the pixel size? Maybe you have gone through sometimes the paper is 1 pixel attack. right? So you generally like classifying some object as a real one, and then someone induced one pixel change, and the model failed at the same time to identify that object, right? So here is also, these are the constraints that if you change the size of my image, the width and height of the image, if I change the contrast level of the image, if I change the pixel size of the image, what will happen? Definitely, all these answer is your model will fail, or your model is going to fail, certainly. Okay? So one of the big problem of machine learning or AI we heard about again when we're talking about ANI is curse of dimensionality. What is curse of dimensionality? Mathematically, what the 1000 image I just explained to you are not sufficient representative for the entire universal set of diffutivity. So in the different conference, or maybe we also talked about by ourselves, that, okay, what is the volume of the data that you need upfront to guarantee that your model is going to survive, or your model is going to be generalized enough? Is it 1,000, 10,000, 10 million? What is the guarantee? Or what is the exact quantity of the data that you need to train these models? The answer is you don't know. Again, we are talking about base error, right? We don't know what is the exact amount of data that's going to satisfy this criteria. For an example, I took a small clip of the microbridge defect, you can see, and the resolution is 512 by 512. This is a grayscale image, so it's one channel. And we know for grayscale, the pixel binning is from 0 to 255, right? That is a distribution of the gray pixel. So to introduce the universal set of diffutivity just for one single clip that I'm showing, you need basically this mathematical figure here depicted by this model. So from one clip to represent your universal set of diffutivity for the single clip, you need this one. And now for 1000 image, you basically multiply this one with this figure, right? Now, if I'm talking about 10 million image, to represent your 10 million image subset or set, or the universal set, you need that metric. And if your channel number is 3, then you have to multiply again with 3, right? And this was basically the interesting case for self-driving car. For the self-driving car, the main problem is that you have enough data to train your model, but you don't have enough data that how many different occurrences of an accident can happen, right? Because we're talking about stochastic event. Okay, this accident is a stochastic event. That is not going to happen like if you take your car 1,000 times in the road. It's not that 1,000 times you are going to meet an accident, right? It can be one out of few millions. So that means when you are trying to teach your model, certainly you are not going to take your car and make an accident intentionally, right? That is not also going to happen, right? So that means if you want to build a model for any application, you have to think about not to develop the model, but what are the challenges that you have to answer or that you have to solve, so that your model can work with whatever the limited data that is possible with you, not for more amount of data. That is not, again, that is because that is not going to guarantee you the universal set of diffutivity, okay? And that is basically defined by curse of dimensionality. The another major problem is catastrophic forgetting, okay? So we know about this problem, maybe. When a human being reads something, it generally doesn't go into your long-term memory. You can only remember the part which has been restored in your long-term memory. But first it goes just like a RAM, right? In a computer, you have a local cache and you have your hard drive or main disk drive, which is long-term memory. So in cache, this is volatile. So similar thing happened with your human brain. You have short-term memory and you have long-term memory. If you read something today, that goes first into your short-term memory, and if you revise it again and again during your whole lifetime, that's generally going to restore in or being stored into your long-term memory. The same happens with the model. So for an example, I took 500 images of line collapse defect type. I built a model. That model is very fine, it's working very fine. But if you follow the constraint, what the constraint I'm putting here is task 1 complete. That means I have detected the line collapse, but I don't have this access to this data anymore. Okay, it can happen that, okay, maybe tomorrow I totally erased all the data and I don't have any availability of this data anymore, right? So if I want to map this model calibration, I can see that model is performing very well for the line collapse. Okay. Now I change the constraint again. Okay. Tomorrow I bring you new 500 images of bridge defect type. This is another defect type. What you can do is, okay, you can plug in the data, you did the training, the model is doing very fine, but again, following the constraint, task 2 is complete, so that means task 1 was complete, and you don't have availability of line class data anymore. Now task 2 is complete, and you don't have access to this data also, like you don't have now access to the bridge and access to the line collapse. And now if I try to map the model performance, you can see that for the line collapse, the model has gone down. For the bridge, it is working fine. So the next day, if you plug in a new data, definitely the bridge is also going down, right? So this is generally defined by catastrophic forwarding. So model-centric approach, supervised or semi-supervised, they are generally limited by mainly to this challenge of these two challenges. One is curse of dimensionality and one is catastrophic forwarding. So no matter what the model you are going to build in future, you have to keep in mind these two bottlenecks. Okay, so a new paradigm has been emerged over the problem is data-centric ML application. That means we're not going to build an idea based on a model, rather the quality of the data that we have, right? So we are evaluating the model performance time to time based on the quality of the data or based on the data that we have. So on the data level quality, you have to follow some strict leveling rule. Okay, I'll show you some of the examples. What does it mean? We have adopted mainly unsupervised approach, and that is basically the generic approach that that the scientists also has started thinking about over the last few years. Okay, there's augmentation. We adopted data augmentation to increase the volume of the data rather than generating digital twins, because as I said, there's always a problem that you are going to introduce some digital artifact, and which is very catastrophic for any manufacturing industry, not only for semiconductor. Feature engineering, we mostly avoided it to not to introduce any bias into our data. So that means we wanted our model to learn from the raw data as maximum as possible. Okay. So what we are doing at IMEC, so we are trying to develop a new Fab AI framework that you are going to plug in your raw data, as I already mentioned, starting from the raw wafer. It goes through, generally passes through all these different rough stages like diffusion, lithography, metrology. My working domain is mainly on lithography metrology. And we are also working with the different collaborators on collecting the data on the HCMP, and packaging is basically what you are seeing in your mobile right now. So we are starting from a 300 millimeter or 200 millimeter wafer, and then you are going to use one chunk of 1 nanometer or micrometer level range of chunk into your device that is holding few millions of transistors, basically. So we are gathering the information, and we are trying to propose a new cognitive model. And you know, like how our brain works, right? Our brain has different modules, different subsections, and generally those subsections integrate each other to make a decision point. So similarly, we're trying to follow the same terminology or same paradigm, that we're not going to propose a specific solution for that one. We're trying to build a knowledge reasoning based on the data has been given to us from the different sections that I already mentioned in a few of my slides before. And based on that knowledge, then you can use this knowledge for any of your problem solving cases, okay, in the different application and decision making. So what we have proposed here is the integration of artificial intelligence and semiconductor process data in a modular framework, just like a human brain we're trying to develop. Okay, so the metrology module is, and which is basically like I'm going to show you some of the examples from this module only, because otherwise the talk will be much more vast and much more broad. It will be beyond time. So we're only talking about same image-based iMetro module. So okay, the user has the raw metro or the litho data. It is plugging into our AI metro module. And based on that one, the knowledge reasoning, we are going to propose the user that, okay, which parameter and features to be significant or extracted or optimized. If you think in your application domain, basically you have done the reverse thing. You basically has decided which parameter or features to be significant, extracted, or optimized, right? Optimization of the engineering tool and cost involved, and always keeping in mind that you have very limited data available. Sometimes you may have only one image, right? What the defects I'm showing, these are the stochastic. So maybe it can happen one. So that means your model has to have some adaptive mechanism to to cope up with this problem that you have limited data availability. Now, again, if I'm going back to our childhood, and if I ask you that how many, say for again, coming back to a very famous Apple, how many Apple images your parents or our parents have shown to us to make a decision that this is an Apple? How many? 1, 2, maximum 10, right? Not in 1,000. So if your brain can make a decision out of say 1 to in a range of 1 to 10 to make a decision for any object, why for the machine learning model or for AI building you need 1,000 of images, right? And the application that we have solved over this application over the decision is image denoising, contour detection extraction, automated defect classification detection, and automated process window analysis. Again, I'm not going to do this, so you can imagine these are some applications that we need in semiconductor. Okay, I'll skip this slide. That is not important so similar for sensor data, right? We have data in two formats mainly. One is image based and one is sensor based. That means you have some signal, and the model can also make the same decisions for this one, and the applications was different, like automated learning of the dependence relation between the each sensor, okay, or anomaly prediction in advance. So basically your model is going to predict that, okay, in the next 5 seconds or in next 10 seconds, some recipe is going to fail or some process is going to fail. So we have enough time in hand to save the wafers to be scrapped, right? And explain why the tool or the process is being drifted. So we are also working in this domain. So so some of the application, and we can see that for the denoiser, okay, we are denoising it, right? And not only that one, this module is also helping you in the other constraint, as you can see here. So again, this is an industry BCAM or industry standard that you generally require 64 frames of integration at least to extract all the information from these images. So again, these are metal lines. So metal lines have a spec. So you can extract all this information. What you have printed is basically from 64 frames of integration. With our denoiser, we have also not only denoised, but reduced this requirement up to 16 times. So which we have developed also a very significant throughput contribution. So that means your tool can work faster. You can generate more number of images within the given limited time, right? And the signal to noise ratio in our calibration, we have enhanced 60%. Okay. On the contour detection, you can see that when we try to extract the contour, you can see that some of the missing contours are there. So one missing contour means you couldn't calibrate the device performance in your spec. You missed. So you can see that how catastrophic that one. And when you can plug in our denoised image, you can see that has been significantly improved. And over that, not only that one, our proposed methodology is also correcting your contour extraction performance over time, right? We have significantly boosted the performance over industry standard. This is a joint patent with Siemens that we have done, and we have seen the gain of 150 to 200%, right? With the human calibration. Or sorry, against the human calibration, not with the human calibration. And what the defect you are seeing here is in generally nanometer scale. So you can see that how our model is generalized and robust enough to detect each and every occurrence of the defect in the nanometer scale here, okay? And the process window analysis means, now if I show you this image and the next image, you can make a decision that, okay, I'm seeing a printable feature, that means a good feature and a bad feature. But if I have to do it unsupervised way, right, how critical that is. So that problem also we have solved, and in 2022, we got a patent for this idea. Okay, so now I'll quickly go through some of the basic concepts before we're going for some application focus, because that is basically to revise your understanding. So this is basically what you are seeing on your left side is basically what is the process, basic process steps that you have to follow if you want to print a chip in a silicon wafer. So you started with a raw silicon wafer, right? You did some of the pre-processing step, again, coating, pre-bake. You have the source of light, that is what you have seen in the tool, what I showed in the video. You have a mask, that means this is basically you generally design in using some EDA tool like Cadence or say suppose like you have designed an AND gate, and that AND gate or OR gate you are going to print into the wafer. So you have to prepare a mask from that design. Okay, you generally expose that design using in the tool some light source. You do some chemical, some physical activities there. Physical activities not by you, but from the tool aspect. Okay, you have a lens, and that lens generally this is driven by physics laws. You know the optics. So I'm not again going through the details of that one, like inference, diffraction, all these things. So you generally going to this lens is going to gather the diffracted lights, okay, of several orders. So this lens can capture zeroth order and a maximum of plus minus one order. All the other higher order, it generally cannot capture. Okay, and I'll show you what is the problem for this challenge. Okay, and then you generally go for the final resist stripping, and you generally etch or generally like print that device into a wafer, and then you can chop a chunk. You do the packaging, and the chip is ready for further electronic device usage. Okay, so this is basically the tool I have shown in the video. Sorry, just a minute. Yeah, this is what the tool you have seen. So this is basically your stages. You put your wafer, and this is track. So track is basically responsible for preparing the wafer for being patterned. So here is a link. So this is basically the wafer is coming here. So these two are jointed actually. Okay, from the track it immediately follows into the scanner. So from here, the wafer is placed here. You generate the UV light, and here is basically you put your design, which is going to be printed, and then doing some flow, that design come and being printed into the wafer. So this is basically how the flow goes. Okay, we call it lithocluster. So track and scanner is basically combined called lithocluster. Okay, now what are the challenges in lithography that we are facing from the past to the future? Transfer mask pattern onto the wafer is a big challenge. Okay, because you cannot follow always the spec which is required. So as you can see here, this is your target CD, and not only all the time you can fall onto the spec. Okay, you cannot always maintain the spec. Sometimes it can go critically wide, sometimes it can go critically narrow. Okay, so we have to define a CD tolerance limit that is plus minus 10% of your target CD. So if you are targeting 20 nanometer, you always have to define a spec 20 nanometer plus minus 10%, and whether all of your process steps are following this spec or not. Okay, so you need this one, but if you print this one or this one, that means your device is basically bad. Your yield is basically has fallen down. Okay, so yeah, so this is mainly the problem what I just explained to you, that if you cannot capture all the diffracted patterns, right? So what will follow is this is your ideal pattern. So suppose like I think many of you have seen this in the EDA design when you design an integrated circuit, the routing, the placement, the device channel emitter, blah blah blah. So if your spec is within, if your process parameters are within spec, that means you have controlled and optimized your process development. The best possible image that you can, again, this is for an example, okay? Best possible image that from this ideal pattern you can get is this one, right? So the mobile you are using right now, which needs this one ideally, but basically it is working with this kind of pattern internally, okay? And that is basically, as I said, your lens cannot capture all the higher order diffracted patterns. It can only capture zeroth and first order maximum, okay? All the other patterns are being lost. And based on that one, the engineers or the tool vendors on the hardware part, so you can see how critical that one to even keep this spec within the tolerance limit. Okay, so traits of Moore's law and Rayleigh criterion. Basically, the Moore's law is driven by the simple equation. CD is equals to K1 multiplied lambda divided by NA. NA is the numerical aperture of the lens you are using. Lambda is the wavelength of the UV light. K1 is a factor that generally, like, we have very few values of that one, 0.22, 0.25, 0.27, and CD. So whatever the feature you are going to print, that is basically given by only these three variables, K1, lambda, and NA. Okay. And that is basically driving Moore's law, and that is going to drive Moore's law in the next upcoming years. Okay. So now, what is the problem? Now you can ask me, what is the problem there? Okay. Now, if you see that, okay, each and every tool has its own defined spec. It cannot, if the spec is beyond the limit, the tool is going to fail to print that device. Now you can see that for this one, 20 nanometer was in spec, and now if you are reducing to 14 nanometer, and this is called hub pitch, 20 to 19, 18 to 17, this is basically we call hub pitch, 13 nanometer. In 14 and 13 nanometer, you can see that this pattern is basically generally crap, right? This is fractured. The fractured pattern you are seeing, so you cannot go beyond the physical limit of any tool and any recipe that has been given to you. Okay. So this is called double patterning. So the concept of double patterning is if your resolution limit, and that is basically like followed by 193 immersion tool, the allowed resolution was 80 nanometer. And you can see here. So the pitch is 90 nanometer. So using the same tool we invented a technique, not we means not me or our team who has invented, it's called double patterning, okay? Within the same spec, what he does is he first printed 90 nanometer, and then he used another mask, okay? So I have used two hierarchical masks, mask A and mask B. Each and every one can print 90 nanometer in pitch. So that means 45 nanometer in is your city. And then we have aligned. So you have to align in such a way that it will be printed if the next pattern exactly in 45 nanometer, right? So I am using the same tool, the same spec, but using an innovative and disruptive technology called double patterning, I can print now using the same tool, which resolution limit is 80 nanometer, I can print 45 nanometer or 40 nanometer, right? So wavelength and the light source are used in lithography. So this is the journey of the light source that we are using since the beginning, G line, I line, and you can see the corresponding resolution limit that is being defined with your chip right now. So right now, all the chips are being printed with 13.5 nanometer, and we cannot go beyond because this is a physical limit of the UV light source, right? So maybe we have to be an Einstein, or maybe we have to be Newton someday to find out what is the next possible wavelength that will help us to print these patterns. But for now, we are close in this growth. So remember, we have three different variables, as I said, which is going to help you to define your next applicable city growth. So you cannot grow, or you cannot do something with lambda. So lambda is gone. Okay. K1 is the physical properties of some materials, just like air, water. So K1 also has no significant chance to be improved. Now, only thing that we can improve is, or the scope of improvement is, if possible, is NA. That means the numerical aperture of the lens. And that is what we are going to show here. Now, this is not a single lens. As you can see here, this is also an evolution journey of the lenses that we are using for this tool. It is a complex set of different lenses, a calibration, optimization of the different lenses, their orientation, their organization, their sequence pattern. So everything has to be precisely controlled. Okay. So, but what we have managed is to increase the numerical aperture of the lens right now. So in UV, we generally followed 0.33. Right now, we are following 0.55. That is the spec we have found right now to keep up Moore's law. Okay, but it has its own, again, it has come with its own challenge. What is the challenge? The challenge is, first of all, the depth of focus. So depth of focus means, as I have shown you in the platform, this is the ideal place where you can place your wafer, right? And in the low NA lens, basically this is your calibration. So as I said, you cannot always reach your target city. You have a tolerance limit of plus minus 10%. For that plus minus 10%, basically it is allowable, or it is allowed to place your wafer in this range. Okay, you can place your range, not ideally, because there is also the mechanical problem is there also, because the stage is also moving all the time, right? You have seen how it is printing. So you cannot stabilize the stage, right? So it is inevitable that your wafer can be placed in any of the vicinity. So within this spec, if you place your wafer, it is expected that your spec is on target. But with the high NA, now this spec is becoming very limited. So that means this range is now the challenge for you. Okay, and that is basically going to affect your image intensity, image blurring, all these ideas. Another problem is the thickness of the resist. So why resist is important? Basically, we don't take the wafer, blank wafer, and we print the device directly on the wafer. In between, what we do is, first of all, we generally coat, maybe some of you know already, have this knowledge. We generally coat with some kind of resist profile. It's a chemical profile. We try to calibrate in the metrology and defect inspection. We generally try to follow that. Okay, if I follow the spec of the process, what is going to be the intended, or what best CD can we print? So that experiment we do on the resist profile, because if something goes wrong, we can always rework. We can just remove the resist top of the wafer or the stack, and then we can regrowth the resist back, and we do again what we have done before, but just by tweaking some of the parameters. But for now, you can see that if we are going to high NA, we have to also squeeze down the thickness of the resist. Okay, so and that is basically thick resist film, and which is now we are going to use is thin resist film. Okay. The quality of same image. Again, you have generally your we call it source mask optimization and illumination, blah blah blah. This concept of physics. So they are generally driven by dose and focus. So you have to find a suitable range between dose and focus that is going to define your spec. Okay. So this is basically, you can see that in the middle is your correct dose, and what will happen if you underexposing or overexposing? What if you have a focus error of your lens? Okay, so this is the correct focus, and you can see. So, and this is so narrow because, as I said, we are talking about nanometer range or micrometer range level of the precision and accuracy. So it is very, very challenging. Even everything is known, to keep your spec within target range is very, very challenging for us. And anything can happen, even though you know upfront that what you are going to do. Okay. And how we do that? That is basically defined by the process window. Okay, the process latitude. So process window means this is your bullseye. That means this is your exact all the combination of the process parameter. But this is, as I said, this is very difficult to land on. Okay, so we have found that okay, if you land in any vicinity with your process parameter, which is defined by plus 10% and minus 10%, so you can land in this eclipse any point, and then you can basically expect that okay, your process is accurate, or what will be the optimization that you have to follow to minimize the error following the spec. That is defined by process window. Okay, so how we are using AI here? I'll quickly wrap up. Okay, so here the problem was, in a given problem, that as I said, we have dose, focus, process parameter, and everything. So basically, this is the target that you have to achieve, but you can have any of these occurrence in your process spec. So now if I come, so someone has to detect which is good and which is bad, right? So again, I'm coming back to a human expert. Now, if I'm coming back to you, for us, it is very, very easy, right? Or as I said, if I'm giving you 200 images, it's very easy for you. That, okay, you are seeing very bad features in the extreme red zone. Green zone is basically what you are expecting. But what if I give you this kind of images, which is bordered by yellow line? Again, if you take your time, think a bit, and you can see that you cannot see a very crux difference between the red bordered image and the how I can say like green bordered image, right? So you can also make a mistake, right? Even though you know all these process parameters, dose, focus, and everything is known to you. Okay, so what we try to do is we try to formulate an unsupervised machine learning model that doesn't know all these different parameters. So I'll just throw the image, and the model can do this dissection or like a difference by itself without knowing any of the BKM or the parameters, what is dose and focus. And you can see that fantastically, and which is we got the pattern, is the model, if you show the image, by seeing and by analyzing, it can give you this proper dissection of the three different regions. So in the middle, you can find always your base features. And base feature is not defined by only one image. Keep in mind, like it can be 10 to 15, because as I said, we have to CD plus minus 10%. And our model, without knowing this is unsupervised, can do that dissection for you. Okay. The denoising. Okay. So this is basically the effect of denoising, as I was talking to you. This is a thick resist thickness, 25 nanometer. And if you want to pattern the same device into the wafer with thin resist, 15 nanometer, now even you can see that how challenging it is for a human being also to extract any feature out of this image, right? You can accept that one. That 25 nanometer reduced down to 15 nanometer is very challenging for human being as well. So why you need denoising? Basically, denoising basically a method that you have the stochastic noise, because if you follow the camera properties of how you are going to take this image out of the nanometer scale device pattern, it basically has to go from different level of primary emission, secondary emission, and each and every emission effect or the tool or the lens effect is basically giving you noise, right? And that noise is basically embedding with your structured pixels. So structure is this one, but you cannot differentiate what is noise and what is structured pixels there if you follow minutely. But we have to remove this noise, okay, out of this, and then we have basically the actual structure that is going to quantify your device feature. Okay, so that is very important. How we can, reduce or remove the noise completely from the device feature. So before us, again, we are not the first one who developed this strategy. But when we did the research, we saw that this is completely supervised. So that means you need a ground truth basically to train your model. But when I'm talking about the ground truth, that means you need 100% noiseless image. And if you see the first line, for the stereosystem image, mostly ground truth data doesn't exist. It doesn't exist. Whatever you do, you can always get some noise level abstraction in your image. So 100% noiseless image doesn't exist, no matter how much try or how much effort you are going to put. So that means if you try to use a completely ground truth noise, that means, again, keeping in mind that you are going to induce some biasness or some digital artifact, we call it digital artifact, that can change the device properties, basically, okay? Some researchers use synthetic noiseless image. You have some software available already, or we have some industry software that basically, if you plug in some image, it generally produce synthetic noiseless image. But again, this is not correct. So, and the synthetic noise, basically, you are going to introduce salt and pepper, poison, and Gaussian noise, which is not quantifying the true metric of the noise you are seeing here. This is more on the gamma noise or random noise, and which has been followed from this research, as you can see here. The Poisson and Gaussian don't fit correctly with the real pixel intensity distribution that we are seeing in this kind of same means scanning electron microscope image that doesn't fall truly on the Poisson side and the Gaussian side. Okay, so what is the point? Okay, so yeah, so we devised an unsupervised mechanism. This is we call it blind spot. Probably some of you have know the blind spot mechanism. This is a tweaking of the conventional CNN training method that we have followed, but in unsupervised way. So that means this model can work with one single noisy image, and we don't need any ground truth to train our model. You can plug in noise image, the model will understand what is the noise there, it will subtract the noise or reduce the noise, and generally you have your output as the denoise image. Again, for saving time, I'll quickly wrap up. So how we have evaluated that our denoiser is working perfectly? Because denoising is not our goal. Our goal is how we can use this denoise image for our further calibration, and whether our denoising is falling into that criteria or holding that criteria or not. So this can be done with the power spectral density analysis. So what is PSD? PSD is basically divided into two different zones. One is the low frequency zone and the high frequency zone. So high frequency zone is basically giving you the idea that what is the noise level there, okay? And low frequency zone means what is your device feature, okay, for line space or for contact hole. And the ideal denoiser will be, after denoising, your low frequency domain has to overlap exactly with the noise image. So if you have your denoise image, and if you have its corresponding noise image, of course, that you have, if you try to plot these two graphs, in the low frequency, that has to be exactly overlapped. And that will guarantee that you have not changed or you have not induced a digital artifact into your denoising mechanism, which all the earlier research method was failed to do. And this is the definition of the noise, as you can see. So this is the noise image, and this is our denoised image. So we have lowered the noise level into our denoised image, right? So that is a validation that we have done with several of our partners and in the industry. And right now, this denoiser is being used within partners. This is the work we have done with Siemens on the control extraction that I have shown to you. So the strategy is very simple: that you are taking our denoiser, you are passing your noise image, you have your denoised image, and now. So we did an experiment, as you can see here. If you take the noise image and use any conventional control extraction like CANI, right? One of the very famous method is CANI control extraction. You can see that on the noise image, you are extracting the controls, but there are a lot of outliers. I'm not sure it's visible or not, but you can see that a lot of red dots are there. Okay, so that means the control extraction is basically failing. Okay, we took the same method with the same parameter and just plugging our denoised image. You can see that how clear or how, yeah, but still there are some of the outliers are there. So what we did, we invented a new control extraction method on top of CANI. And basically now you can see the result is completely fine. And when you are plugging in that one, you can see that in the noise image, that outlier is also gone, as you can see here. Okay, so we completely reverse engineer the process of any data pre-processing, because as I said, if you do some data pre-processing like the Gaussian blur or median blur or any of the known method, that basically is good for, those are not the noise removal technique, though we have a misconception that those are noise removal technique, but those are basically noise smoothing technique, not the noise removal technique. So with this idea, we have changed that conception of noise removal rather than noise smoothing. Okay. Yeah, I'm just skipping this slide once again. So that's what are the added advantage that we bring into this method. What is the time now? How much time I have left? Okay, I'm skipping these things. Okay. Okay. Let me skip some of the slides to save some time. I'll directly jump on some interesting fact here. If someone is interested, you can. These all are publicly available research papers are there, so you can directly follow. Or if you have any question, you can always like shoot your question in the email or there. Okay, so this is, I'll show you some of the examples on the defect inspection. Okay, so what are the challenges in defect inspection? Mainly, as I said, is the variability on the defect origin, the contrast change, the pixel value change, the image and the field of view change as well. So we have seen that all the current mechanisms are failing to, not on the defect inspections. Okay, as I said, on the application, you can build any application. Basically based on machine learning model. But how generalized and robust that model to cope up with the industrial challenge, that is basically our research strategy. We are trying to solve the application by mitigating the challenges of that problem. Okay. So yeah, machine learning is inevitable in that one that we already have shown. And basically, we started with supervised. As you can see that, okay, someone has to annotate the image, and you can train your model, and yeah, you have your desired results. And basically, this is a framework of how the model is working. So you have the images. So this is an ensemble method. So what is the ensemble method? That is more interesting. So now, if I come back to this part, and I come back to the audience, that, okay, I have 3 different models. That is basically what I'm trying to establish with the model-centric approach. So model-centric approach means you have 3 different models. I'm taking the ResNet family, 50, 101, and 152. Okay, I have 5 different defects that you have already seen. And now if you see the performance, okay, and the overall performance, you can see that, okay, I have 78% for ResNet 50, 77% for ResNet 101, and 152 is 78%, say. And you can see that for some of the defects, it is performing really, really poor, right? For ResNet 101, for probability of gap, that means when your metal line is becoming narrowing down, you can see it is only 29% or 37%. So if I come back to you or come back to anyone that, okay, what is the resolution that you can give me that I don't have to throw a model, right? Because again, the new model, whatever I will take, there's also no guarantee that the model will survive this criteria. So exactly what we developed here is that concept in terms of ensemble method, that we're not going to throw any of the model. The strategy is the model will adaptively evaluate what is my voting in terms of voting, right? So we are assembling the voting strategy of each and every model for each and every defect. And based on that one, it is taking an adaptive method how to enhance my previous failure to a more success. And you can see that we're doing that. We are sustaining what is the model's, say, best average accuracy, and we are also improving each and every model's performance into a new one. So that means you have boosted, say, with this ensemble method, without throwing any of the model and sustaining with a challenge, we can improve certainly from 30% to 52%, right? And overall, if you think about overall, also it is improving the overall challenge, 78% to 81%. Okay, so that means this is the data-centric approach rather than the model-centric approach that we have adopted. Okay, so we started, like as I said, like this is a continuous research that we are doing. In the next part, what we have done is how we can improve the, and this is basically what we have shown for the model-centric improvement. If you take the different models on the same challenge, keeping all the different constraints same, you can see that is a different performances there, right? So with the model-centric approach, we try to improve, and definitely we have improved 10% on the overall performance by using Dino. But yeah, it is continuous, right? Like each and every year, each and every quarter, maybe you have a different kind of model, which is definitely surpassing all its previous one. So this is basically the, you can think of the advantage of using model-centric approach. But again, this is not sustainable in industry. So we tried with the data-centric approach. So one of the data-centric approach is definitely different, like data augmentation and optimization methods that we have to follow. Okay, but remember, like as I said, all these metrics are generally published for real-world data, like COCO, Pascal, VOC. There was no like fact check for our kind of data, because this is very, very different. But I said that this is very, very close to medical data. Okay, same semiconductor data and medical data. The challenges are mostly same, but they have different varieties on the challenge. So we developed our own mechanism of augmentation strategies. We developed our own mechanism of optimization over the years. One of the advantages also weighted box fusion. I'm not sure how many of you know. Non-max suppression means that, like, okay, I'm throwing say like depending on how many anchors you can throw, say suppose like 30. What NMS does, NMS will take only one out of the 30 different bounding box based on the classification score, right? But scientists have said that, okay, you cannot throw any information. Maybe that information, why your model has thought all the other possibilities of other 29 and additional one, that you have to think. So they invented a new strategy called weighted box fusion. And basically you can see what is it. So this is basically what your model is showing. And you can see that this is mostly accurate. The NMS will take the most accurate one because this has the highest probably the classification score. And weighted box fusion is basically adjusting. So it is taking all the different voting consciousness from the different boxes, and it will give, or it will produce a new kind of totally new bounding box, which is more accurate. Okay, and by doing so, you can see that from 81%, by utilizing the same method and same constraint, we have gone up to 86%. Okay, so when it was individually 77%, with the ensemble method, we improved to 81% or 82%. With our strategy, we have improved the similar problem to 86% till now. Okay. Okay. The segmentation on the part, again, this is nothing new, but yeah, in our case, you have to keep in mind that we are doing it in nanometer scale. Okay, the segmentation is nanometer scale. Why it is important? Because as I said, the attribute of line collapse, or attribute of bridge, or attribute of any other defect, okay, they have this interclass. So line collapse, bridge, probability of gap, micro bridge, they are the interclass defects. So this many defects we are seeing, but they can also vary by themselves. Okay, you can have different precision or the different extent of line collapse by themselves. So this basically is helpful for the root cause analysis of what physical properties has changed within the tool or the recipe or why the tool has been drifted in the hardware part that is basically originating this defect. So this kind of metadata is important to reverse engineer the process steps for the process experts or the tool experts. And that is basically we are going to help them with this kind of segmentation method. So you can see that, okay, you have plugged in an image again in the nanometer scale, and we are just, because the neighborhood is not important for us, okay? In which region and what extent of defect has appeared in which nanometer scale range bandwidth is more important to us, okay? And we are precisely generating the segmentation for them. Then, of course, like for any invention you always have to, how I can say, improve. There's always a scope of improvement, right? So the one problem that we have followed is, and basically like Mask-Carcerian was not designed for segmentation. Okay, if you have carefully gone through the paper basically improved by using mask or the region proposal network is basically improving the detection task. Okay, and basically that was a problem. In the segmentation, again, this can segment, but segmentation was not so precise. And you can see one of the example for the, so we have some kind of bulge is appearing in between two, which is not accurate, right? So, and you can see, so the new method we have invented, again, the point trend we didn't invent, but yeah, semi-point trend we invented is to correct that fallacy of our previous model with a new proposed method called semi-point trend. So this is kind of a rendering algorithm, pixel-wise, and it can identify, okay, and you can see that the fascinating part is there also. The model can basically segment truly what is its true extent in polynomial form, okay? And again, the improved story is, as you can see here. So from our previous model, without throwing, because semi-point trend is based on Mask-Carcerian itself, we just have changed the algorithm strategy. And you can see that from 54%, with the data-centric approach, we have improved to 61%, which is 13.8% of improvement in the segmentation task. Okay, ongoing work is okay. We have taken line space. This is what you are seeing is called direct assembly. If you have remember my one of the first slide, I told you that there you have three different strategies generally to keep MOSO alive. One is high NUV, one is double patterning or the different patterning methods, and one is DSA. So this is basically is a resist profile you are seeing here, and with the help of light source, right? The structure is reorganized by itself. Okay, so we generally don't need a mask or lens kind of thing. We just use a light source with the chemical properties of the resist profile. The formation of this structure is automated. Okay, but here also we have the origin of the defects, which is like say close patch. But here what we did is fascinating. Is we give the same data to different levelers, and those are anonymous. We did an experiment ourselves because say suppose if you also think about yourself in place of them, and if I give you this data to all of you, definitely you are going to level, if you don't have any ground truth instruction from the expert, definitely you are going to level this defect and the extent of the defect differently. Okay, your bounding box can never be similar as my extent of the bounding box, or your naming convention can never be the same as my naming convention, and that is basically you are seeing here. So this is the original image, and this is leveler A, and you can see that what is his leveling convention. So he leveled and here keep in mind nobody is totally wrong. Okay, so and leveler B is leveling in this way. Okay, so we invented a method that can auto correct the human level error. Okay, and you can see here. So this is the human annotation you are seeing here. Okay, now if I come back to you and ask you that, is there any possibility that this leveler has done something wrong, and can you see some other occurrence of the defect if you follow minutely? So this is the human annotation. So that is the best a human or the expert has done. I have two different instances of probability of gap and two different instances of gap. But if I come back to you, that is it correct? Can you see any other possibility of any other occurrence of the defect? Yes, no? At least that is what you can answer, right? Yes, I'm seeing a defect, or no, I'm not seeing any other defect. Anyone? Okay. So at the inference level, now you can see that the model is unfortunately missing one of the occurrence of the defect that has been labeled by the human, right? In that case, what is possible for us? We cannot do anything. Maybe we can try with a new model if I am following the model-centric approach. But again, as I said, that is not possible when you are working in an industry. Okay, so we have to do, or we have to invent some kind of mechanism that only not going to correct model's performance, but maybe it can also judge if the human has labeled it correctly or not. Okay, and that is the example that we are going to see here. Right. So we've developed a new strategy, which is not only correcting the previous model's performance, but also it is challenging that, okay, the human expert also didn't do his job correctly, right? So I can see more instances of the defect in terms of PGAP, which was more challenging for us even, like which is very critical. Right, so that is what we have also built, and then also you can see that we built a reinforcement learning agent that can identify the defect automatically. So if you throw an image, this agent with the reinforcement learning can analyze all its context, and it can correctly build a bounding box, unsupervised way. Okay, I'm seeing some abnormality has happened in this vicinity, and it is auto-correcting its bounding box placement. Okay. Yeah, so we have also the future scope, as you can see in my screen. Conclusion is AI's integration into semiconductor manufacturing is an unprecedentedly forward, and not only for semiconductor, but also for your own applications. You can use by yourself how wisely you can take into AI's contribution or AI's application to your own domain. Okay, and that's all. Thank you. Thank you.
Yes, sir, I'm present. Definitely, sir. Thank you for the opportunity. Good evening, everyone. My name is Shubhra Baroi. I'm the Assistant HR at Abacus Institute of Engineering and Management. It's an absolute honor to deliver the vote of thanks at the conclusion of this enriching session on behalf of the organizing committee and all participants of the ATOL Faculty Development Program on semiconductors. I extend my deepest gratitude to Dr. Bapaditya De for sharing his expertise and insights with us today. Sir, your wealth of knowledge, drawn from your extensive research, numerous publications, and patents, has truly inspired us. Once again, thank you, sir, for your time and for enlightening us with your cutting edge research. We look forward to more such insightful sessions in the future. Wishing everyone a wonderful evening ahead. Thank you. Thank you, sir.
Thank you. Thank you, everyone.